And he was like, well, on TiVo, that was or DVR, not TiVo. Well, grow up. It's 2013, get DVR. Or internet.
I don't think internet is quantized, Elijah.
It is. It was invented. So that means it's quantized.
I'm pretty sure it's
Nope. It was invented by them. So
anyway,
Yeah. So he was like, I'm going to see masterpiece deal with that, which is so great. It's called Mr. Selfridges. And it's about the biggest, Selfridges is actually still the biggest department store in the world. But like the original guy, Mr. Selfridge, he like lost it just before he died, like because he spends like an asshole everywhere he goes. But the show is about the startings of Selfridges. So I was like, I'll watch it. The first episode is interesting, but not quite the quality of fucking down. But you can tell it's gonna get there.
Such the opportunity.
Yeah, and the UK has already had full season of Selfridges, so you can get online and watch the full season.
All right, guys.
It's just down so much. What's that supposed to be?
My girlfriend says she's
There's a couple different ways to do this, but I kind of agree with the book, and also I think I might have skipped this earlier, but if I have a general triangle here, it's not a right triangle. It's one of those situations where you could draw in a height and kind of make some right triangles. But I want to find the area of this triangle directly, just using things involved in this triangle. So I've got this angle here, angle A, okay, angle B. Good, I'll let you just angle A. Angle A, angle B, angle C. I've got these sides, and notice how this is something we're going to do very often. We're going to have angle A here. Angles are normally capital letters. And right across from it is the associated side, so it's going to be the lowercase of that letter. Right? Okay. Amazing. But it just makes it easier to reference what the hell's going on. If I wanted the area of this thing, it's going to be the half, 1/2 the base times the height. And the base is C. Well, that's nice. And the height, I don't know what the height is. I actually have a couple different ways I can get that height. If I use angle A, I'm going to look at this right triangle here, right? So one way to do the height is to look at A, and what can I set up related to A that would give me this height in terms of the sides and the angles?
B, C, the base.
Yeah, the sine of A would equal H over B. So H would be B sine A. Is that cool? So that means that this would be 1/2 C B sine A. But what if I use angle B to figure out what the height is? So I'd still use sine. Sine B would equal, now I'm looking at this right triangle, H over A. Yeah. Again, nothing groundbreaking here, but okay, yes, sir.
Is this thing in the book?
Yes, it is. This thing is it's actually back in the end of 6.3. Yeah.
How are we getting the signs? The signs, like the sign.
How are we getting them? We are writing them down. And I'm not even. Well, I am sort of trying to be a jerk, but the real answer to your question is, the real question you're asking is, why do sine A in the first place? How does it help me? Well, the whole point is, I don't know what H is, and I want it based off of what I know. But I do know that sine of A is H over B. Then I can solve for H. Then I know what H is. But I could have also at the same time done sine of B is H over its hypotenuse A. So then I get H is A sine B.
Why didn't you write it like cosine over B? Like cosine B?
Because I need H, and H is the Y part. So cosine's not going to help me. I really don't care about this piece or that piece. Right? Not currently, anyway.
Good.
How we doing so far?
Yep.
Now, I could turn this whole triangle around and do it again. I would still get, so here I would get 1/2 CA sine B. So just remember, 1/2 C was kind of set up for me, 1/2 the base. I just didn't know the height. I could write the height like that, or I could write the height like that. And if you turn the triangle around, just to kind of cut to the chase here, you can also write this as 1/2 AB sine C. If you make B or A the base. You guys got to follow? If I just turn this bad boy around, do exactly what we just did, you can get that. What this really leads to, now, that by itself is useful. Right? And in general, what that really says is, notice what that says in any of these cases. If I know, if I have a triangle, I take this side times that side, cut it in half times the sine of the included angle. Let me say that again. When I say that word included angle, does that make sense? If I have two sides, I inherently have an included angle. So if I use the sides C and A, the included angle should be B, and that's exactly what's there. Are you with me? So that idea of included angle is very useful. It's going to come up every now and again. All right. So here, in this case, let me see where I want to go with it. Well, let's see. I like this here better myself. These two tell me that B sine A equals A sine B. Which, if I rearrange it a little bit, becomes very easy to memorize. Sine A over A equals sine B over B. If I do something similar with the C business, I get, incredibly enough, sine C over C. How does that feel? Now, I should always be able to capture the stuff we knew before. This is, believe it or not, this simple little dude is the law of sines. I should be able to recapture something from before. So, for example, if C is a 90-degree angle, let's see what I get if I just apply the law of sines directly. If C is 90, then it says sine A over A equals sine C over C. Sine A over A equals, what's sine of 90? 1. Sine A equals, multiply the A up. Are you guys kind of with me a little bit? So I'm using parts of this rule. And I'm saying, what if C was 90 degrees? I should be able to recapture what we already know. And sure enough, what's the sine of A supposed to be? It's supposed to be A over C. That's exactly what I got. So this is a more general rule than what we've known so far. Now it works for anything, even if it doesn't have a 90-degree angle, it works. But when is this useful? What kind of triangle situations? So what I mean by that is triangles where we know some parts of it, but we don't know other parts of it. This is really kind of cool as far as when to know when to do what. So one big part of math is I know how to do that, Jeff. I don't know when to do that. Dude, that happens almost all the damn time, every day. You guys have that situation happen. And here, this kind of kicks ass. I can only use this rule when I can actually create one of these ratios. If I don't have an angle and its side, if I don't have that anywhere, I can't create one of the ratios. I can't use this. So the two situations this kind of goes with are the one that I already told you was SSA. That's the leads to trouble.
Right.
Right. And the other one is the, they give it two different ways of saying it, but I just like to say ASA, angle, side, angle. So this would be angle, side, angle. Those two I can use with law of sines. Would I memorize that? Hell no. I just know that I can only use law of sines if I can create an entire ratio. Because then I can set up another ratio just leaving the part that I don't know, just leave it the variable. So let's do a concrete example. Let's see. Let's do one, not the weird one. Let's just do this one first. So let's say I have a triangle, and triangle like this is 10. This angle is 35, and this angle is what do you want, Jeff? 20. All right, so what they might say in the book would be something like C is 10. A is 35 and B is 20. This is supposed to be little c. So this will be A, B, and I've got little c. So why is this a situation where I can use law of sines? What's one complete ratio that I can make? And a complete ratio would be an angle and its related side.
Because you can know C's.
Yeah, I know what C is. What's C got to be?
Whatever makes that add up to 180.
180, I love it. So we got 55 so far.
125.
125. So I know C's got to be 125. You put little angle things there. So the question of when do I use this, Jeff, is easy. You use law of sines when you can actually make this ratio. If you can't make that ratio, you use law of cosines. And the really cool thing is they work exactly like that. Whatever sines can't do, cosines can do. Thank the Lord. Or whatever deity you are. So what can I set up here? I can make this complete ratio sine C over C, and then I can do whichever one I want to. So let's do sine A over A. So then I can use that to figure out what? The length of A. That's the only thing I'm not going to know there, the length of A. So I fill in sine C was 125 over side C is 10. A is 35. On side A, I have no idea.
You do it in radians all the time, or degrees? You do it in
Right now, you have to
percent?
do it in degrees, whatever this is. Yeah.
Or you could just do the conversion of
So what do you guys get roughly? Oh, yes.
So we got this position e to a times sine 125 equals 10 times sine 30.
Sure, you could cross multiply. Sure. Reciprocate both sides and then just multiply the sine 35 up. Does that make sense? Yeah, any way you do this should work out. Yeah, you get just about 7, almost exactly, 7.002 something. I wish I could claim that I actually did that on purpose, but I didn't. So A equals 7. So really, the instructions on this kind of problem would be solve the triangle. Now, that before today, it'd be like, what the hell? How do you solve a triangle? Is that a song from Sound of Music? What the hell does that mean? Well, what that means is figure out all the angles you don't know, figure out all the sides you don't know. That's what solving the triangle means. So what else? What's the only thing I don't know left? Sine B. So then I can do the exact same thing, but just using sine B over B. No big deal. Let's finish that out. So I know all this stuff here. That's sine 125 over 10. That's this guy. Sine of B, which is 20. Over little b. So what do you guys get for that?
4.175.
Yep. B is about 4.18. Now, why does it make sense? What's the largest side?
C.
C, and that's across from the largest angle. And that opens more than that, and that side is a little bigger than that one. I mean, that all kind of goes together, but opens more, should fit more side in there across from it. That makes sense. Thank God. Okay. So you got some checks and balances there. Let me let you guys try one out on your own. And then we'll tackle one of these. Alright, so what if I tell you? So again, you know this is law of sines. Currently you know it's law of sines because that's the only one we're talking about. But here you know it's law of sines because you can make that ratio. Now I can figure out what A is before I figure out what angle B is. Side A, side B, side C. But of course, what's angle B anyway? What's the easiest thing to get out of this? Yeah, so we already have 45, so it's got to be 135. Cool. And then what ratio can I set up?
Sine C over.
Yeah, sine of 25 over 80.4. And now I can go whichever way I want to. Yeah, sine of 20 over A. Cool. So that gets A equals 80.4 sine 20 over sine 5. Yes.
Where does the sine 20 come from, sir?
Right there. So I'm using sine C over side C equals sine A over side A. Right? I know every one of those except for side A. So I can solve for side A. So it's almost just too easy. I think a lot of times students don't trust it when it seems too easy. It's like, nah, he just made it look easy. No, it's easy. It really is. Let it be easy. What do you get when you throw that in the calculator?
That's terrible.
I don't think you want that, do you?
I don't want it.
I gave it to you before you.
So nice. Say it. 65.07? Why does it make sense so far? Or does it make sense so far?
Yes.
Cool. Why?
Smaller than C.
Yeah, that opened up a little bigger than that did, and that's a little bigger than that is. So far, it makes some sense. So it really makes sense. Side B should be bigger than either one of those because it's the biggest angle on that side. So I just have to set up the same kind of ratio, sine 25 to 80.4. And now I can do the B, sine 135. It's a little B dude. So it's relatively easy mathematics. Right? It's built off of trig values. We had to build up the idea of getting out of 90-degree triangles into more general triangles. But these signs still represent the same thing they did before. They still represent those ratios of signs. So here B equals 80.4 times that divided by that. What do you guys get for
134.5.
134.5? So you know you're done with the problem when you get all three sides, all three angles. The triangle has been solved. Cool. That seems easy. So let's look at the more complicated case. Remind me, what's the output? What's the range of inverse sine?
Angle. 0 to 180.
Now, if I said, what's the output physically, then an angle would be a good answer. What's the range? What's the range
0 to 460.
of the inverse sine?
Or 0 to 5.
So keep in mind, the sine is this dude here. So remember what we have to restrict the domain of the sine itself to make it invertible. It's got to pass the horizontal line test. So I wanted to make it start here and end there. So this would be negative pi over 2 to pi over 2. So the range of inverse sine is going to be negative pi over 2 to pi over 2. So if the actual angle in your triangle is supposed to be 120 degrees, it's never going to come out of this. Does it make sense? So why am I saying that? Because this other case is not this. You're going to have not enough angles. You're going to actually have to eventually take an inverse sine to get there. So you've got to be real careful about what comes out of inverse sine. And that actually is really why it leads to the ambiguity. This is why it leads to two possible answers. So here's conceptually why there's two possible answers. So if I have, so our problem is ASS. So if I know an angle and two sides, so let's say I know this side, and I know how long this side is, and I know this angle. So this is one possible answer right there. It could be this here could be the answer. Or another answer would be, if I swing this bad boy in, swing this in, maybe another answer would be there. So I'm trying to construct a triangle, and I'm given a side, another side, and an angle. And it's not in the right place to really constrain things. There might be two answers to this problem. There might be two ways to do it. I can swing it out here, and there's one answer. The last side, that I don't know how long it is, would have to be that long. Or I could swing it in. Everything stays the same. That's just as long as it's supposed to be. That's as long as it's supposed to be. That opens up as much as it's supposed to be. I just swung the dude in. That's a whole other possible answer. There could be no answers. Is never going to connect. What can I do with that? This guy's got to go out there. Oh, there's no way. That's going to have no answers, right? Or there could be one answer where it's like exactly the right size. I can't swing it anywhere because it just went straight down, just connected. There's no swinging involved. You guys kind of with me? So it could be no answers, one answer, or two answers. So the next question would be then, how the hell do I tell which one is which? Well, the no answer one is easy. The first thing you do, it comes out to nothing. There's nothing to play with. There's nothing to change. It just says nothing. All right, crap. You come out to like, why would this be an example of no answer? If I get inverse sine of x equals 1.72. Why would that be a problem? Why would that indicate a problem? What's the largest output sine can have? 1. So this is saying what angle has an output sine 1.72? Right, and actually I got this turned around, don't I? Good head. There you go. So which, that can't happen. So if I get an inverse sine of a number bigger than 1 or less than -1, that's obviously not going to lead me anywhere. That would be an indication that it's no answer. So that one's going to be pretty easy. It's the difference between one answer and two answers that's going to suck. Right? Yes, sir?
What's this situation if the dangling side there is so much longer that it swings out wide, and it also swings back to the other side of the angle that we know? Does that make any sense?
It can't do that because this angle is set to be here.
Okay.
So it can't be long enough that you have to swing it way out there. But if it's longer than this one, then that's going to be a case where you only have one answer. Does that make sense?
Yeah.
Yeah. All right. So let's see what this looks like. So let's say angle A is 43 degrees. So A is 19 meters, and B is 4.5 meters. So I already know that it's going to be a law of sines case. Before I draw anything or do anything else, how do I know that just looking at this? C specific. Yeah, I have an angle, and it's, careful now, not just that I have an angle and two sides. In that case, it would lead to that, yeah, but I can make a ratio, right? Sine of this over its associated side. I've got an angle and its associated side. So I know it's got to be some kind of law of sines. I don't see yet why it's going to be an ambiguous case. You just got to realize this is angle, side, side. That's the key, right? It's like, oh shit. Could be more than one answer, no answer, something freaky. So, the picture you draw doesn't have to be, obviously, does not have to be beautiful. It can always be the same triangle. Doesn't truly matter. Here's your A is 43 degrees. Side A is 19. And side B is 24. So here's side B, here's side angle B, angle C, side C. So we'll all have this. Just some of us might have a mirror image, or some of us are turned around a little bit. Doesn't matter. Just set up where your sides are, where your angles are, and make sure they're across from each other. Now let's just start attacking this like we know we can. We know we can make a ratio, so we do that. So what ratio can I make? In this case,
Other sine and other side, right?
yeah, the A's, I can make that ratio. So I got sine of A over side A. And now, there's only one way I can go with this at the moment. B? Yeah, I've got to do B because I don't know a damn thing about C. So sine of B over side B. How are we doing so far? Yeah? So now you can see, in this case, I've got to do an inverse sine. And inverse sine has this funky range. And that's really what leads me to some of this trouble. So see what we get here. Make sure you're in degrees. And I haven't said this, but you guys notice how when you hit the sine button, at least in the older TIs, it opens that parenthesis for you? I hate that. Just make sure you close it. That's what I was doing earlier. I kept forgetting to close it. And I, no. So what are you guys getting for B? Are you guys in degrees? And make sure when you put it in. So to get this, you can actually do the inverse sine of 24.5 times sine of 43 over 19. You guys see that? That'll get multiplied up, and then I take the inverse sine of both sides. Is that cool? What you should get, I think I heard it over here, 61.57. So make sure you get that before I move on here. Yes, ma'am. Oh, so I multiply this up. So sine B equals mess. Inverse sine of both sides to solve for B. Yeah. Is that cool? Now here's the trick. I so far have at least one answer. Because I got that, and then I can figure out what C is, and then I can make the ratio and figure out what side C is and all that kind of stuff. You with me? Is that cool? The fact that it's an ASS situation, ASS, you have to check to see, could this be a reference angle for another angle? And does that angle work with the one we already know? So let me see, what the hell did I just say? If this were a reference angle, realizing this is a triangle, what are the only two quadrants that our angles could really live in? First and second. Can't be bigger than 180. So if this were a reference angle, what angle would it be referencing? It'd be here, so it'd be 61.57 here. So what's this angle here? Yeah, 119 or 118.43. Does that work? What do I mean by that? Does that work with the 43-degree angle? No. What does that really mean? Do they add up to 180 or more? Then it's no. What's 118.43 plus 43? So it works. What would be an example of it not working? If this was 160 plus 43 is bigger than it can be. Let me say this again. So you get one answer directly. No problem. You love it. That's awesome. What's going to suck is if you don't get the other answer also. So how do you check to see if there's another answer? That might be a reference angle. The output for an inverse sine is not necessarily the actual angle. It's got a very limited range. If my answer is more than 90 degrees, what can this inverse sine do? It can't do shit. It can say, here it is. Please see that it's... So it says 61.57. The answer could be bigger than 90. Shit. So what is this then? A reference angle. So if the reference angle gives me this answer and it works with this, it doesn't add up to more than 180, then that's a valid other triangle. That's where the side can swing in. So this angle here could either be 61, or it could be big, or it could be 118.43. Do you see that? If I swing it in, it's small, whoop, and that's big. That's exactly what this here means. Yes, ma'am.
So you check it every time
Every time you got an ASS, an SSA, whatever way you look, you gotta check that. If it was a no answer, obviously we would have gotten no answer right off the bat, which means we can't even check, so that's a no answer. That's easy case then. You gotta love that. Doesn't work? Beautiful. No answer, go to the next one. One answer would be that this does not work with this. Awesome, you just gotta finish this guy out. So we're in the worst case scenario. This is where you guys, a lot of you are at least as messy as I am. And a big key to this kind of problem is organization. You've got one whole set of answers based off of this angle, and then a whole other set of answers based off of that angle. So you got angle B1, and you have angle B2. In both situations, what do I not know yet? Yeah, side C and angle C. You with me? So then I can say angle C1 would be what, and angle C2 would be what, and then I got to figure out side C1 and side C2. So it really shouldn't be that difficult to organize yourself. Number one, check to make sure there's another answer, and number two, if there is, make sure you get all the answers for both separate. So what's angle C1 if B1 is 61.57? What would this angle here be? You got 43 so far. Plus the 61 is 104.57. How much is left over for the last angle then? Yep, 75.43. You guys cool with that? That part's nice. I got two angles, so the last angle's easy enough. Just make them add 180. Sweet. How do we get side C1? Yeah, now I know angle C. I can make the ratio. So I can say sine 43 to 19 for the A's equals sine 75.43 to C. And figure out what sides. Well, let's make it C1. And the work you do for the other one is going to look exactly the same as this, except you're going to be using that 118.43 angle. Not too difficult, right? I can tell on some of your faces it's not very interesting either, but that's all right. So here I get C1 is, well, let's see. What are you getting for C1? It's almost exactly 27. Yeah, it's almost exactly 27. 26.96. So that triangle is solved. This house is clean. Yeah.
Would you ever dock this if you rounded it when it's that close?
Especially not at the very end. But if you take something like this angle here, to be truly technical, right here you should really use the, like right here should be this whole thing, but we've rounded to two places. That's going to throw everything off a little bit. But if you round to like 75 here, this stuff is going to get thrown way the hell off. You understand? Yeah.
How do you set up sine C1 with the inverse sine?
Oh, to do the inverse sine? You couldn't, because you need angle C to figure out the side. And if you don't have the side, you can't make the ratio. There'd be too many unknowns.
Would you use the inverse sine?
right here to figure out B. Thankfully, you only have to use it once. Because the minute we use it, we know 2 angles, so therefore we know 3. Yeah. So in the second case, angle C2 would be what?
18.7.
Yeah, 18 point something, so it's 43 and 118 is 1, blah, 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 so you get 18.57. Alright. Sounds about right. 137, yeah, cool. So again, just making 180 degrees in that triangle, right? And then how to get C2? The same way we got this. C2 sine 43 19 equals sine of 18.57 sine C2, and we solve for C2. Again, very often the work itself almost seems too easy to trust. You're like, yeah, it's got to be harder than this. But I don't know if you guys are thinking that at all. Or maybe you're thinking, what the hell is he talking about? It's hard enough. So, let's see. I get for C2, what do I get? Yeah, I get 8.87 meters. Cool. So just like solving an equation could have 2 answers, could have even more. A triangle can have 0, 1, or 2 answers. Only in this case they count. The other cases will have just the 1 answer. It's only this case that's the ambiguous case. Okay, so what about law of cosines? See how much stamina you guys have.
You.
What's that?
It's you. It's all you.
No. I can go all day.
Oh, sorry.
I'll just crash really hard that night, but don't worry, it's not a threat. To figure out the law of cosines, I want to take a triangle. It's not a right triangle. In fact, let's make it even worse. Let's make it a triangle that kind of like goes back on itself a little bit. Basically going to do what the book does here. So let me see, maybe we get the same. So what I'm trying to do here is, I want this law of cosines, I want it to relate the sides in a more general way than the Pythagorean theorem does. So what I'm going to try to do is figure out the lengths of the sides based on the other 2 sides in a more general triangle. So for a 90-degree triangle, it's easy. A squared plus B squared equals C squared. So now I'm trying to do the same kind of thing, but with a more general triangle, a non-90-degree triangle. So I need to know these points so I can figure out distances between points. Really, right? So this is going to get slightly funkadelic, maybe. This is angle A here. Angle C, angle B. So I want to know what point that is based on everything I've written so far. Let's give ourselves an angle. Well, we already got 3 angles. What would that point be? When I've drawn this in, I've made it a little bit easier. If I know what this side is, that's the X piece. This will be the Y piece, so that's easy enough. This is a nice right 90-degree angle, thank God. So part of this derivation depends on 90-degree triangles, that's cool. So what would this be here? Now let me help you out a little bit. This angle here, what would that angle there be? Yeah, that would be 180. Oops. It's horrible. 180 minus A. Is that cool? Because the whole thing makes 180 degrees. Right? So sort of, maybe, not really. Okay. Okay, so what is this side here then? In terms of the angles and sides in that triangle. What is this side here? What ratio do I want to set up? What's the only side that I really feel comfortable with in that triangle? This triangle here, this right triangle. What's the only side that I feel comfortable with? I love it. A is not in this triangle. B. That's the only thing I got. I got A, B, and C, and the only one that's in this triangle is B. Right? So how can I, what ratio do I want to set up that involves this side and this side? What trig function would I use on this? Cosine. Cool. So I've got cosine of A, not A, cosine of 180 minus A equals this side, let's call this X, over B. Cool. So X equals B cosine of 180 minus A. Now here's a really nice thing about cosine. If I'm at an angle, let's say A, 180 minus A would be where? Let's say this is A is 10. What's A? 180 minus A? It would be back here, right? So the really cool thing is, this X should be negative, right? So I would get the same value if I just used the angle itself, A, but it's just got to be the negative of that angle, right? What we doing so far? A little bit? All right. So the really nice thing is, if I use just cosine of A, won't the cosine of A itself, won't it be negative? Because that's back in the second quadrant. Won't the cosine of A be negative? And I want this X to be negative. So the really funky thing about triangles that bend back on themselves, if I want to know just this side, it's going to be the cosine of that angle times this, because I want it to be negative. It's got to be leaning back on itself. So I want that side to be negative. So this side is just going to be B cosine A. That's the X piece of that point. This is going to be, so far I know that this is B cosine A. Now I just want to figure out what this side is, so I can figure out the Y piece of that point. So I do something similar, and hopefully we can maybe get there a little bit quicker now. If the X piece is B cosine A, the Y piece should probably be B sine A. Because I can make that same ratio, Y equals, sine of A equals Y over B. So Y will equal B sine A. So that point is B cosine A, B sine A. This point is easy enough. What's this point? Hopefully. Your brains aren't too fried for that. I pretty much gave you that point. How far away from 0, 0 is it? How far away from 0, 0 is it? C. So it's got to be C0. So I got the point 0, 0, B cosine A, B sine A, and C0. Okay. So by the way, they do this derivation on page 476. So, what's the how far apart are these 2 points? So the distance between them is A. So the distance formula, I don't know if you remember this. Distance formula was that guy. Does that look at all familiar? It's really, again, it's really based off the Pythagorean theorem. So if I put in the points here, I know that a squared, a is the distance between the points. What are the points themselves? Well, the x parts of the points are b cosine a minus c plus b sine a minus 0. Just plugging in the points that we've got. That's why I had to figure out those points, so I can use a distance formula to figure out what the distance was between them. That's going to relate the length of this side to the lengths of these sides. That's really what I want to get here. So if I play with this a little bit, such as just foiling that part out, squaring that last part. Now here's a really cool thing. This happens a lot. This is going to happen to us a lot in chapter 7. This is going to happen to us a crazy amount in chapter 7. Do you guys notice anything I can actually do something with here that I can actually combine in a way?
The basis.
B squared cosine.
Yeah.
B squared sine.
These two. B squared cosine squared plus B squared sine squared. If I take a B squared out, what do I get?
Sine squared.
Cosine squared plus sine squared, which is 1. So I get B squared times 1, so I get B squared. What is it supposed to be? B cosine. Okay. Did I miss anybody? C squared? Oh yeah. I knew I left out that little plus C squared. You guys see that? I got lost in the purple. Yeah.
Where'd the 1 go?
Oh, B squared times 1. So just B squared, yeah. Is that piece okay? Take a B squared out times cosine squared plus sine squared. That's 1. That kicks ass. So now I get, let me see if I can get this together. I get, if I solve for, well, let's just do this. A squared equals B squared plus C squared minus 2BC cosine A. And I want you to realize this A, B, and C, weren't they arbitrary? I mean, I could have just named, I didn't care which side I named A, B, or C. So the funky thing is, this could have also been B squared equals A squared plus C squared minus 2AC cosine A. Oops, yeah. Cosine B. This could have been C squared equals A squared plus B squared minus 2AC cosine C. And this is what I was talking about earlier. This last one is the one that's more close to what we think of. And even then, A, B, and C are just arbitrary, but this is the one that's, there's the Pythagorean theorem, and there's the adjustment piece for the general triangle, not just the 90-degree triangle. Because what's cosine of 90?
1.
Careful. 0. Cosine of x at 90 degrees, there's no x, so cosine of 90 is 0, so that's when it becomes the Pythagorean theorem, when that C is 90 degrees. Yeah?
Sorry, I'm just going to ask you to go back. And when you added together b squared, cos squared, a plus b squared, sin squared, a.
Yeah, so
That second
take a
one.
b squared out,
Oh, okay.
and what's that is 1. Yeah. Sweet. So this, collectively, is the law of cosines. And actually, it's just one thing there. It doesn't really matter what you call A, B, or C, but you just kind of do it depending on what they give you. So notice how it's always two sides, and then here's the included angle. Or even better, if that's A, that's A, and then these are B and C. I mean, you can kind of see the pattern. Yeah?
When you do a concrete example, could you leave that part up so that like connect the completely abstract.
Well, the problem is, this is, how do I say, sure, I can leave it up there. But this is using the distance formula to get something that relates to the lengths of the sides. That's not really at all what a problem given to me is going to look like. Does that make sense? We're using a distance formula. A problem's not going to care about distance formula. It's just going to say, here's the lengths of these sides. Yeah?
Just to make sure that bottom of the c squared, that's c squared equals a squared plus b squared minus 2ab. Right?
2ab, that's right. I got C happy up there, yeah. So it's always got to be BC, BC, AC, AC, AB, AB. If that's C, that's C, that's the other. So it's just Pythagorean theorem with a little adjustment. So let's try a concrete example and then we'll probably head out. Can I take a picture off, maybe? Is that all right?
Yeah, that's fine.
So this is the situation. Now this would be something I can use for side. Like. And the really cool thing about law of cosines, there's no ambiguous case because the output for cosine, inverse cosine. I don't know if you guys remember. So cosine was this dude. So when we went to restrict its domain, we restricted from here to there. So we went from 0 to pi. That's exactly the angles that are going to show up in a triangle, right? From 0 to 180 degrees. The law of cosines leads to no ambiguous cases. It gives you all the angles you need. That kind of kicks ass. So it's a slightly more disgusting formula, but the trade-off is you're not going to have disgusting outcomes. So I could have a problem like solve triangle. Well, if something actually works here, that might be good. So I got to be careful when I put these together. If I was trying to create a triangle out of a 2-foot and a 7-foot, this side could not be 9 feet, for example, right?
Maybe that's right.
Because then it would be a straight line. There'd be no space for it to be a triangle then. And this side could obviously definitely not be 10 feet, because then it's like trying to open wider than it really is. Right? That's not a good idea. So I do have to be a little careful about what I give you. So I give you 2 and 7 makes 9. It's bigger than 8, so that should work. There should be room for that to happen. So now you could do anything you want to do here. Any of these, because you know A, B, and C, so you can solve for any angle that you want to. And the minute you have an angle, what can you do? If you do the law of sines, and I kind of set you up for this, you might bring in the inverse sine giving you the incorrect angle, right? So it's really up to you. I know that the largest side is going to have the largest angle. So I would probably go for doing cosine C. I don't know if you guys are really going to get this, because then I could trust my sines to give me the right stuff. Maybe that works. Well, let's try it out. Let's do the one that's going to give me cosine C, so I can figure out the largest side's angle. So it'd be c squared equals a squared plus b squared minus 2ab cosine C. And now you just got to plug and chug. And yes, you still have to memorize this. We have not hit the point where you don't have to memorize something yet. That's chapter 7. 64 equals 4 plus 49 minus, twice 2, 7. And again, why does this make sense? Well, let's see. We'll wait and see. Do you see how you're going to come out with like a negative result for cosine, that just means that its input is bigger than 90 because it's going to take it back into negative x territory. Does that make sense? So here I get 64 minus 53. You get 11. Divided by negative 4 times 7, negative 28. Is that cool? I always get people suddenly forget order operations on this problem. Which is worrying. Don't do that. I always get 4 plus 49 minus 2 times 2 times 7, and that's the coefficient for cosine C. That's magic. All right? Don't do that stuff in here. So subtract 53, divide by negative 28, and then I have to do what to both sides? Inverse cosine. So take the inverse cosine of negative 11/28. Don't forget the negative sign. So what do we get for? Yeah, 113.13. Does it make sense to anybody why you should go ahead and attack the one that's going to come out to be the biggest angle? Because then if I do my inverse sines, it's not going to give me an ambiguous case. I've got the biggest angle figured out already. It's never going to work with another angle. I don't know if you guys really get what I'm saying. I've got the one angle I've got itself is already 113 freaking degrees. It's not going to really work with the reference angle for some other angle. That was a neat sentence on that. It's not going to work with the other dude's angle. Okay. So let's try to finish this out with sines and see what happens. So what do I have so far? Now I know angle C. So now what ratio can I make for sines? Yeah, sine of 113.13 over 8, beautiful, equals sine of A over 2, for example. Because I don't know A or B, doesn't matter which one I pick. A equals inverse sine of 2 times that over 8. We double it to the inverse sine. Inverse sine of sine of 113.3 divided by 4. Reducing that if you want to. What do you guys think? 13.39 roughly. Cool. It's if this was a reference angle, it's the angle it's referencing would be 167 or 166 point whatever. Ain't no way it's going to work with that. That's what I was desperately trying to figure out how to put together a sentence that would say that.
Did that first and found A first, and there'd be a ton of different things that would work.
Beautiful. Exactly. So that's my suggestion to you. Either do the largest angle first, or there's nothing really wrong with using law of cosines several times. Actually, I only have to use it one more time, but does that make sense? Because law of cosines will never itself lead to an ambiguous case. Law of sines, its outputs don't really work.
That just takes more time.
It takes more time. Exactly.
You know, solve for B2 now? Oh.
Yeah, so we're not quite done yet. A is 13.29 and C is 113.3. The only thing I don't know yet is angle B. So it's got to be 126.53.58.
Yes, sir.
Thank you. And now it's solved. We got all three sides and all three angles. That's probably enough. Just to warn you guys, both of these sections, there are problems that some of you might consider word problems. But all they really are can you take what they tell you and draw the picture, and then it becomes this. It's not a word problem. Sometimes they draw the picture for you. Yay. Sometimes they don't. Shit.
What sections are we going to
6, 5, 6, 6. So we did manage to finish out chapter 6. Chapter 7. Look at you guys. I'm such an evil person. Just real quick, chapter 7 involves, that's really where I'm talking about, you have to be comfortable to play around with stuff. It's where we're going to be trig identities. We only know really one that led into 3. Sine squared, cosine squared equals 1. Chapter 7, the amount of identities we know is going to just grow exponentially. We're going to know, I'm going to pass out next time, just pass out. I'm going to pass out a thing with all the identities on it. I'll tell you exactly which ones you have to memorize and which ones you don't. No, not for the quiz. The quiz actually only goes up through before graphing. There's no graphing on it either. Yeah. Exactly. Exactly.